So to understand Knuth-Bendix completion, there are three essential steps that we need to understand. The three essential things that we need to understand. So the first one will be the order of complexity. So now we will let this greater than R. Okay, so this greater than subscript R. So from now on, I will just say greater than in complexity. Okay, so to be defined, so to compare complexity, I put inverted commas because we will not be defining the complexity in in a more formal formal definition between terms. So what we can see is that complexity is some sort of measure of length or size of the term. So for example, in A1 to A4, we have the equation 0 plus x, okay, then it will be greater than x in complexity. So over here also x plus 0 will be greater than x in complexity, and lastly over here we have greater than 0 for negative x plus x to be greater than 0 in terms of complexity. Okay, however, if you look at this one for the A1 to A3 is quite simple, quite easy to see that the left hand side has more symbols as compared to the one on the right hand side. However, if you look at the right A4, they are both sides have the same number of terms, same number of variables and symbols itself. So whenever this happens, for terms of the same side, we view the terms as tree and compare the complexity of the leftmost subtree. So for example, if you look at these two, okay, if you view them as tree, okay, you can see that on this side, the leftmost subtree over here is less complex than the leftmost subtree over here, and hence we would conclude that this will be more complex than this. Okay, so whenever there's a tie between the same size, okay, we will view the expression or term in terms of tree, and we compare the complexity of the leftmost tree. So with this, okay, with the order of complexity set, and now we can introduce this rewrite rule. So what do I mean by rewrite rule? Whenever I write t arrow t prime, okay, it means that t and t prime are equal to each other, and t is more complex than t prime. So for our axiom A1 to A4, previously the group additive axiom, we can change all of them to rewrite rule. So over here we will have, instead of 0 plus x equals to x, we will write 0 plus x arrow x. Okay, so same for all other, depending on the order itself. So now I'm going to introduce another term, which is normalization and reduction. So what is it? It's a process of repeatedly applying rewrite rules to a term. Okay, if no rule can be applied to a term, it is said to be in normal form. So for example, we have this complicated expression or complicated term. We use R3 to simplify, so this is one of the rewrite rule, R3 to simplify this to 0, then use R2, okay, to simplify to negative a. Then from this point on, we cannot use any of the rewrite rule, okay, to continue and simplify it even more. So we will say that this will be the normal form of this expression or this term. So now I'm going to introduce a property of the rewrite rules. So a set of rewrite rules R is noetherian if each rule L arrow R in the set of rewrite rule capital R satisfy L greater than R in the complexity with the following properties. Well-founded, so which means every non-subset S of T, which is a set of terms we use in the theory, okay, or in the language, has a least element or the minimum element with respect to the ordering of greater than in complexity. Next, you need to be stable. What do I mean by stable? So if T prime is greater than T double prime in complexity, under substitution of variables inside each of the terms, okay, the complexity preserve, the complexity still preserve under substitution itself. So for example, maybe with example, okay, by the way, for this one, whenever this is the notation for substitution. So t prime square bracket t slash x means that for every occurrence of x, okay, in t prime, we replace by the term t. Okay, so this stable means that if t prime is greater than or equals to t double prime, okay, with any substitution, common substitution of the variable, substitution of the common variables between two terms, the complexity is still preserved. So let's look at example. For example, with x plus y is greater than x in terms of complexity, and if we have the term t equals to a plus x, and we substitute the x, all occurrence of x with a plus b, okay, and this will still be at will still be greater than the right hand side in terms of complexity. So the complexity preserved under substitution. So next, monotonic is slightly different from stable, but it's similar but it's different. So I'll go through that. If t prime is greater than t double prime in terms of complexity, this implies that if t prime is substituted to a variable x, okay, in some term t, okay, it will be greater than if the same term is substituted with t prime for every occurrence of x. Okay, so under substitution, if you sub for the same term, if you sub these two t prime and t double prime, the one that's substituted with t prime, which is the greater complexity, will the resulting term will be still be more complex as compared to the one that substituted with t double prime. So it may be a bit complicated. Same. Let's look at the example. For our case, for this case, t let a plus b, it will be greater than a, and our term t, okay, the general term that we are looking at, t is x plus 1. If you sub x with a plus b, and we sub x with a, the resulting term, okay, by substitution with a plus b, will be more complex as compared to the term that's substituted with just a itself. Okay, so this is called monotonic. So a set of rewrite rules are Noetherian if these three properties hold. Okay, so what are the advantages of having Noetherian rewrite rules? Okay, so this will greatly decrease the space of possible application, and the space is finite due to the well-foundedness. So what does it mean is that instead of having the initial without the rewrite rules equality, if we recall, suppose that machine need to reason this out again, okay, if we don't have the rewrite rule, we can go from right to left, left to right, and sometimes you can go in a loop. So for this, you can equate to this can equate to this equate to this, and equate to this, or same over here. So whenever there's no, whenever you try to write from left to right without order of decreasing complexity, it will make the space of all the proofs to be relatively larger than those as compared to because when you rewrite, you go to lesser complexity, and due to well-foundedness, you'll keep moving towards less and less, or at least same complexity from whenever you write from left to right. Whereas for this case, you can go more complex or less complex, and it may go in the loop. Yeah, so the space, okay, so the space of proofs will be finite, okay, and it will be decreases due to these rules. And all variables that occur in the right hand side of a rewrite rule must also occur on the left hand side. This means no new variable will be introduced into terms as they are rewritten. So this means that this sort of guarantee that the complexity will only decrease or remain the same after every application of rewrite rules. Okay, so now we're going to introduce the two proofs that we're going to look more into it, to discuss it throughout this paper. So it's rewrite proof versus non-rewrite proof. So rewrite proof is when both sides of the theorem, for our case is equation, reduced to the same normal form, okay, that does not contain a peak. Later I'm going to explain what is this peak. So for example, we want to prove this left hand side is equals to the right hand side. Okay, so we reduce this to a normal form, reduce the right hand side to a normal form as well. If both normal form are the same, okay, we will say that these two are equal and this is a rewrite proof. Okay, how can we conclude that this is equal? Because remember the arrow implies that they are still equal, just that the complexity, there's difference in complexity. However, they are still equal. So this means that if you go here to here, is this equals to this equals to this. And we go from here to here, is this equals to this equals to this, and this equals to this. So eventually, this whole chain will be all equivalent. Okay, and we have the same normal form, so we can conclude that this will be equals to this. Whereas in non-rewrite proof, okay, we cannot, for example, we want to prove for negative A equals to A. Both are at the normal form. We are unable to continue writing a rewrite proof. So what we can do is we do a reverse from left hand side all the way to the right hand side, and at the same time achieving a peak term over here, and we call it the critical term. Okay, so how do we do it? Okay, so negative A, we're going to check whether what are the possible rule that can get to here. So one rule is negative plus A, then over here. So keep going up. So it's sort of a reverse rewriting. Okay, so from less complicated to more complicated, but then we just keep track of the arrow sign. Okay, so we go up until we hit a peak. Then after that we try to narrow down. Now we try to reduce it and see whether it will eventually hit the right hand side or not. For this case, yes. If this is the case, since we are unable, these two are at the normal form, and we achieve this proof by reversing to get a peak term, which we call it the critical term, and moving down to by reducing to get a normal form. And same thing, if this equals to this equals to this equals to this, and we know that this will be equals to this will be equals to this, so eventually we can conclude that this will be equals to this. Okay, we can show that this shows that negative A equals to A. However, this is a non-rewrite proof because it will this is how we define it, and they have contain at least one critical term. Okay, so discovery of these critical terms are important, but how are we going to generate them? Because after all, this is quite a simple equation that we want to discover whether is it true or not. Okay, so and we only have one rewrite, and we have 4 rewrite rules that we can play around, so it's relatively quite easy for us to go up and go down. Okay, so but as the equation is get more complicated that we want to try to prove, then moving up to find the critical term and trying at each point we want to see whether it can normalize to this right hand side, okay, can be quite complicated, and it may take a very long time. So eventually our goal is to generate a set of rewrite rules such that all theorems, which for our case the equation, can be proved by rewrite proofs. So eventually we're going to make use of all this critical term, okay, in our algorithm, okay, that eventually it will all cancel out. It will remove all the rewrite proof, and eventually every proof for the theorem will become a rewrite proof itself. Okay.